So all of these examples we've got on here are examples of where convection is our primary method of thermal energy transfer of heating from something which is hot to something that is cold. And taking them in turn, we've got radiators heating up rooms, which kind of makes their statement of their actual name being a radiator as being incorrect. We've got the reason for sort of weather patterns, so the reason for sea breezes, when you've got the difference between land and the ocean. You've got the heating of water inside a saucepan or a kettle, if you wish. We've got the convection currents, so the convection that exists in the mantle, which distributes energy from the core out to the surface, the crust of the Earth. And we've even got things that are going on in the entire ocean. The entire ocean is a giant conveyor belt led by convection, which transports sort of energy between the warmer waters around the equator to the colder water that you get, that's out towards the poles. And that all of these are about redistributing out the energy, this idea you've got somewhere which is warmer and somewhere which is colder, and trying to distribute that energy out. Sort of a natural process. So convection, the thing that links all these is that they are not solids. These are always liquids or gases, which is basically what we call fluids. Okay, so a fluid doesn't mean just a liquid in physics or engineering. A fluid is anything where particles are free to move about, move over each other. But that's not a term you necessarily need to worry about. So convection. Convection is the main method of heating in liquids and gases. Okay, and our idea of conduction, why doesn't conduction happen in these things? Well, conduction happens in solids, where the particles have to vibrate and bounce into the next particle. But in liquids and gases, they can just freely move over each other. So conduction, isn't able to happen through this, so we end up with convection. So how does it occur? Well, it is when it occurs due to the movement of hotter, more energetic particles to colder regions. Okay, so let's consider why this might occur. Let's think about something like a humble candle. Okay, so let's say we've got an example of a candle. Now, surrounding this are air particles, and those air particles are all over the place. And what they're going to do is, by being close to this source of energy, they are going to gain more energy. By gaining more energy, they move more. Because they move more, well, what they do is they will spread out. So these particles won't be close as here, but after we heat them a little bit, so after we've sort of increased their temperature, what they will do is they will now sort of occupy the same number of particles, but they're going to occupy a bigger space. So same number, I can't count that number of dots, but the particles are spread out. So we get the particles spread out. And what's clear, and this is where we need to make sure, we can't just say the particles are not becoming less dense, because the particles themselves, but what we've got is the same amount of mass, but now in a bigger space, and the air becomes less dense. So this is now less dense than, say, some colder air, which is sitting on top of it. So we've got, let's say, we've got our sort of like, there's our normal air, which hasn't warmed up yet. Well, this air, because it's close together, more dense than this air. And if you remember doing density in year 9, well, this doesn't happen. More dense things sink, okay? Less dense things float on top of more dense things. So these particles, well, these particles have got to go upwards. So these particles now have to move because they are less dense, so they will rise up. We'd help if I did this properly. So what happens is they will move up and sit on top of it. So they move upwards, which what that means is that, so I'm going to put that over there for a moment. Well, we've now got a gap. So what's going to happen? These particles will actually get buffeted up by these ones a little bit. So what will actually happen is colder particles from the sides will swing in. And this is what sets up this kind of cyclical current, because then the particles that swing in are going to get warmed up and they're going to go up. And then they're going to be replaced by other ones. And so what you end up with is a cycle being created where wherever you've got your source of thermal, your source of sort of energy, where the thing is hot, those particles will become less dense, they will rise, and they get replaced by ones that are more dense. So we can think about why this occurs in these sort of different areas. So around a radiator, that's pretty easy. You hold your hand over a radiator, it's above it that's really, really warm. And that's because these warm particles are going up. And it's below it that you'll get cold particles will come in. On the Earth itself, the sun shines on the Earth, but there are different things that happen. Partly it's because of the tilt of the Earth, giving less than different amounts of daylight in different places. But even around the equator, you've got two things that the sunlight is warming up. Land, which tends to heat up very quickly, and the ocean, which heats up more slowly. So you end up with a temperature difference between the air. The air above the land gets warmed up, so it goes up. Get replaced by cold air coming in from the side, from the ocean. And it's why you will always, in the daytime, if you go stand on a beach, you will always feel a sea breeze coming in from the ocean. What's quite lovely is that actually at night time, this whole situation reverses. When the sun goes away, turn the sun off. Bye-bye, sun. If you turn the sun off, it goes nighttime, the ocean actually cools down more slowly. You might notice if you go, if you've ever wandered around a sunny beach, when the sun's out, you'll notice that sand gets very hot very quickly, whereas at night it cools down a lot. It's why it's why it's okay often to actually go swimming, later on in the evening, because the ocean's been absorbing that energy from the sun the whole day. The ocean is now the warmer thing, and so you actually get a convection current set up the other way around, where it's now the air above the water is slightly warmer, and so you end up with an offshore breeze. Inside any sort of cooking element, sort of kettles or on a gas stove or anything, you'll heat up the water just above where the flames are, where the heating element is. That will become less dense, will go up and go round. And same is true under the surface of the Earth. The thing that's hot, well, it's the core. The core is exceptionally hot, it's molten, and you've got this huge amount of energy that's sort of really from the Earth still cooling down from when it's regenerated by radioactive processes. That energy gets transferred out because above it is a sort of a liquid mantle where the particles are able to move around. And that motion as well, if you do geography, is also what leads to the motion of tectonic plates in the crust and leads to various things like earthquakes and volcanoes and so on. And even across the ocean itself, we have different sort of densities, and this is called the thermohaline system, because it's to do not just with the temperature, which is obviously warmer in the equator, colder at the poles, but also to do with the salinity. Different parts of the ocean have different amounts of salt in it. So areas which are saltier, they become more dense and they actually fall down and become lower. So you end up with cold and salty current very deep down, warmer current on the top, which is slightly less salty, and that ends up with the thermohaline thing. And this is something that is obviously at risk, potentially due to climate change, because it's a sort of fine balance of differences in temperatures. But the entire ocean is a big heat engine to move energy away from the equator and to the poles, which is actually one of the reasons why, due to climate change, we see a more dramatic impact at the poles more rapidly than we do elsewhere. So that's what convection is, and all these different examples of things going on. But the principle is always the same. Okay, and I'm going to just sort of lay it out. So the steps of convection. So the convection key steps that we have. Okay, the first thing is that the particles are heated. Okay, which means that they, or say they gain energy. Because they're going to be moving more. So they're given some source is going to give them kinetic energy. We then end up with the particles spread out. And this therefore means that depending on whether you're talking about a liquid or a gas, the liquid or the gas, okay, don't use the word particles here, because if you've got sort of an oxygen molecule, making the oxygen 5 degrees warmer doesn't make the oxygen particle itself. The oxygen molecule doesn't get less dense, but the oxygen particles are spread out. So the liquid or the gas becomes less dense, so it rises and is replaced by colder and denser liquid or gas. And then 5, this sets up a convection current. So this is what's going on, and it's responsible for huge vast amounts. All weather on the Earth is largely initiated by this idea that you've got somewhere which is warmer, and therefore you get this temperature difference, which leads to things moving around. So all of this, so many phenomena across the globe occur. Predominantly, this is the reason that it's occurring. And those are the key steps that you need. If you're asked to describe a convection current, this is what it is. And it's about spotting, if you get a question, it's about spotting, okay, how do I explain what's going on and why? And just simply about that. But that is how convection sort of works. And what I want you to do now is to watch the video, which takes you through a lot of just demonstrations of convection currents being set up inside the lab, so you can get a sense of what is going on. But each single time, and I'll probably repeat it a lot in the video, these are the steps that are occurring.